And then we have Matias Alonso Crespo, a design industrial designer, talking about virtual surgical planning of patient-specific implant solution from a perspective of design for manufacture. That is very interesting, I'm sure. Are you ready, Matias?
I am. Everything fine,
Okay,
Ron? Thanks.
nice to see you. All right, take it away, Matias.
Okay. I will try to speak slowly so it becomes very clear to understand.
Yeah,
So, I will talk in a little bit about virtual surgical planning. I am an industrial designer, so I will try to approach from a perspective of design for manufacture.
okay.
As I told you, I studied industrial design. I work in the medical fields for 6 years now. I work as design consultant, actually. I do freelance for VSP and PSI projects. I do medical visualizations and renderings, and I am most of all a 3D generalist modeler. So my webinar is more focused on concept behind design, mostly specific for design for manufacture. The expectations are you to understand which are the technology limitations and possibilities, how to improve your design depending on your material and process requirements, and see a little bit of an anatomical model optimization for if FFF production. So before getting to from design for manufacture, I will ask to you what is design. So design is the process of finding a solution to a specific problem. We have a problem, we have an initial situation, and we have a solution, a desirable outcome we have to achieve. Design process is between them, and you have to do research, plan, validate, and test all the solution before going to implantation, right? So, as my background is more focused on industrial design, I will try to bring some concepts from human-centered design, where we have three main factors or areas we can work. The desirability is where the human needs are all the users are here. The not only the final patient will be being plated, also the surgeon will be using this dispositive, and why not the manufacturer partner as another user of this system, right? The viability is where the views needs are. Here are the marketing things, are the business model. This here are also the very important regulatory, all the regulatory stuff, and we have finally the feasibility sector. Here are all the technological needs. Fine, the manufacture of materials, process, and selection for make the solution happen in real life. So, may you ask how virtual surgical plan is involved in design for manufacture? So why should I know this if I'm not producing it? Most of design engineers are not well familiar with production process, so they are designing solutions in computer that are not well optimized for production. This happens a lot, and we have an iterative process between manufacturing and design has to be respected, and we have to go from one side to other side to understand and to work better with optimal solutions, right? So when we start talking about PS implant and surgical guides design, we have to think in principles of good design. A good design of implant is clinically functional. This is really important because clinical decisions are always on top of the design decisions. We have to follow always the clinical decisions made in the well-being of the quality of the patient's life. So user oriented to the surgeon is utilizing. So it has to be understandable. It has to be clear to use, and you cannot miss without using this dispositive. It has to be optimized. All the technology has own limitations and opportunities. So the design has to be optimized in that direction. Has to have an organic shape. Organic shape because actually we see in a lot of in internet solutions that are really pretty on the screen, but when we start thinking, they have a lot of corners, rough edge that the human body doesn't have really. So we have to work with less invasive implants and solutions. We aim to achieve better fitness of the surgical guides and implants without having to extend the superficial of the implant. We have to even less extend the surgical access of this surgery. So we have to achieve the compliance. It's important to achieve regulatory terms, and it has to be feasible. So it has to be manufacturable, and most of all, it has to be validated. This cannot be passing away. So we have to validate all the solutions we are planning. In we have simulations, or we can do test productions, and prototypes, so we can achieve better validated solutions. So always think that we have to follow these good design principles to achieve better outcomes for the patients and the surgeons using the dispositives. So let's make a quick example with biomodels replica. So anatomical biomodels. We have most common virtual surgical approach. So we have a CT exam, we take the informations, we made our segmentation, we create our lower jaw 3D model, we export it as STL, and we send it to print, but it's really optimized for FDM print or FF print. We take this STL, we take it to the Mesh Mixer software. This is an open source software. We take them here. We can see the jaw model now moving. When we toggle transparency on, we can see all the anatomical structures inside of it. These are a thresholding result of the segmentation process. So we want to achieve a full-filed watertight model. I will explain how this will work and will help with the production process. So again, we have a 3D model previously segmented direct from DICOM data. We toggle the transparency on, and we can see all the anatomical structures inside of it. So what happened when we are going to production? I run a simulation on Ultimate Cura. We can see upside is the segmentation model, downside is the optimized 3D model generated. So we can see that we are going from 8 hours production of the segmentation direct model to 4 hours and a half for the optimized model. So when we make a comparison of this process of this treatment of models, we can see we can achieve almost a 45% time reduction, almost a 30% of material reduction, and of course less on sexual prints. So these simulations were run on Ultimate Cura. I use all the standard parameters, and 15% of material infill and 10% of added supports. So this is a process. It's easy to make. You don't need to own a printer to make this. You can download always the software and make a test. So moving forward, what happens when we go with a big model, a complete head school? So we can pass from 2 days of 3D printing to 1 day on 10 hours from optimized model. So this is a FDM rule. I have to say it's a rule that works really nice with when we have models that are fully filled and are in one piece, but don't necessarily applies with SLS, SLA, polished technologies, or even multi-filament new machines. So uh, works when we have a fully unique model, but when we are going to more visualization 3D printer, we have to work with structure anatomical independent elements, so we can give them a right color, a right texture, a right material, and be really clear when we show it. So it's all about materialization. When we think, for example, in additive manufacture, we could think is 3D printed with FM, SLI, SLS. We are printing resin, we are printing titanium, or we are printing even PIC. So every technology has its own limitations and opportunities. It's really important as a design engineer to understand these limitations, opportunities, so we can optimize the real final design and achieve the better results and outcomes for the patient. So how to know, right? There are too many process out there, and how to know what I have to use when I have a case. So I would like to starting ask to your client or to your manufacturer representative sales uh, how the device will be produced. So we can start orienting the design to that process specifically. We can simulate the process. As I told you, you can download there are plenty of software you can download to simulate the indicated manufacture process. And to improve the outcome, you can make a interaction design process where you can adjust the final aspect of your design to get really optimized. So you can also ask for reference when it's a complex process and you can simply just simulate the process. You can always find a person in LinkedIn, for example. There are plenty of salesperson working in companies that are really willing to produce for you, so you can use them. You can send a test file, of course, and you can estimate your cost, and you can estimate if the tolerance and all the manufacturer capabilities are being treated and taken care. So finally, you have to research and validate. Always, every solution, every design have to be validated, and it has a research background behind. So we don't want to just giving design ideas, just thinking will be for the patient a good choice, but we have to validate and risk validate all this information. So what is design for manufacture? Design for manufacture is about following this principle. So we have a material has to be available, has to be suitable for this patient, and it has to be accessible. It doesn't work for a patient to have a really 3D fully titanium printed cranioplasty implant if they cannot afford it, or if they live in a remote place that they cannot access to that technology. So it has to be completely suitable and accessible for the case and the situation. We have to select a process. The process has to be optimal. Has to be cost effective. We have to always look the cost side of this whole system. We have to think in volume production. We have to think in tolerance. Every technology has the only limitations, and as I saw, so we have to start thinking that we have to follow all the tolerance and aspect of every and each technology available. So we have to make a validations. Here are the simulations, the prototyping, and the testing iterations. So it's important to get a fully validated design before getting implanted to the patient. We have to think in environment as context of use. If we are making a mark on a dispositive, it will be legible on a context with corporal fluids on it. We have to think all the situations it will be passing through. This implant will be sterilized, so the material has to follow these rules. So we haven't any issues during the production process. So we have to achieve compliance. We have to stay inside the regulatory field. We have to think in standardization components. If you are using another standard element, we have to guarantee these elements will work in the system. And finally, we have design. Design is about conceptualization, is always user-centered, and have to achieve simplicity and work with the assembly phase of all the product design process, so we can achieve a really good result. So benefits. The principal benefit of DFM is to improve the product with a cost reduction. The reliability. Designing and following the rule of the specific manufacturing process always guarantee accuracy and reliability to the virtual planet model. And we want to have a physical model that represents the digital model in the best way, in the most reliability way. So it's a work opportunity because VSP can be integrated in different levels of implication, from 3D image reports to a complete PSI reconstruction. So understand these requirements of your client, of your patient, of your available technology will allow always the best feasible solution for the conditions given. So about the material and processes, I will make a really quick overview so we can understand when we are talking about subtracting manufacture, we are talking about starting from a material box, and we start carving and milling and machining it to get the final result and the final model. This has a lot of waste material because we are literally carving and throwing out all the undesirable elements and materials. So we have an additive manufacture which is adding material layer by layer, point by point, just enough to get the final model and final piece. So there are really less waste than in a subtractive method. And we have a conforming manufacture. That is a combined manufacturing process that allows to achieve conforming operations to bring the results and to achieve the final model. So how to apply this concept or these manufacture concepts in PS design. So we bring us this design process diagram. So we have an initial problem, we have a recasted solution, and we have in the middle a design process. When we talk about initial problem, we have a bone cranial defect, we have a shape reconstruction as outcome desirable, and we have in the middle, of course, a design process of a cranioplasty. So I will try to approach this design of this implant from a perspective of manufacturer. So I won't be arguing if there's a material that is better than other. There's a lot of materials and they have their own properties and advantage and disadvantage. That's disadvantage. So it's important to understand that I only focusing in manufacture process and I'm not putting on the table the design aspects of an implant. So There are a lot of surgical decisions have to be made with the surgeon responsible. So just to clarify this concept. So when we talk about subtracting manufacture, we can think, for example, in peak, we can research, we can validate, we can find a lot of articles validating the use of this material and the process. This could be also titanium or could be solid PMMA. So it's about the subtracting manufacture method. We have a CNC machining, a carving process. These are materials available, and it's more characterized for high precision outcomes with really tight tolerance. So we have a solution. When we think in peak, they are extremely high tolerance affected. So we can start working in bipartite fitting parts or elements in our implant. We can make the texture or embed the standard plates to the implant. We can make holes for despressurizing, and we can embed also the screws into the implant. So when we are embedding screws into the implant, so they are completely high, we have to think in a split way of this portion, right? If we make a sagittal split of this portion here, we can see we are leaving a really tiny mixed material here under the head of the screw. So we have to treat design to optimize this part. So we have an optimized part. We are guaranteeing that we have always the same thickness around the head. So these are things that we can achieve with subtracting manufacturing process, with 3D printing also, but we will see later. So additive manufacture, we have, for example, a titanium 3D mesh. This we can again research, find some articles. We are talking about 3D printing. We are talking about peak materials, and we also are talking about titanium materials. So the main particularity on this process is about to achieving complex shapes. So we have a solution. When we think in titanium, we think in organic shapes, volumetric meshes. We are thinking and talking about lattice structures. We can integrate the fixation plates into the implant. We can work with lattice structures, as I saw. We can work also with embed screws, and we can make different surface finishments. Always remember that 3D printed titanium metals and peak materials also, they have a post-processing step. So they normally went off with a raw surface. So we have to think in this aspect before delivering our final design, because sometime we will have to compensate these post-processing steps so we achieve the desirable result. So, and again, thinking now in conforming manufacture, we could think a titanium 2D mesh with a conformation. We make our research. We are talking about a combined process with CNC subtractive wave and conforming press wave. We can do this for titanium, also for PIC, and it has a benefit that is cost reduction, and is really, we can really achieve low profile. So we have a solution. In this process, we can achieve really nice, well, high detailed patterns. We can achieve really low profile implants, and we can work with perpendicular monocortical screws. So all the technology has their advantage, and we can optimize always the design in that way. So again, we are thinking in other technology like PMM molded. This is a conforming technology of as we have a 3D printing and combine it with a molding phase. We can print the 3D molds and we can achieve a result also. In this case, it's a simpler implant because it has to be moldable, and we can go directly with printing the molds so we can achieve really high accuracy and precision. So which are the conclusions? We as design engineer, or I as a design engineer, I think I have always to think in design process. This is a user-centered process. We have to always think in the patient, and the surgeon is using the dispositive. This is a concept driving, so I have to follow good design principles to make to bring my solution to the table. I have to think in a manufacturer driven way. So I have to think always this has to be achievable and has to be feasible. So um, we have to research and validate. We have our responsibility. So it allows also the traceability of the design process. If we have an issue in the upfront in the process, we can go back and see if the were a decision problem, the design decision problem, or it was a manufacturing process problem, and we can try to fix this in a iterative way so we can achieve better results. Also, we are guaranteeing that our design is inamovable. If I am sending well suited for a manufactured process specificity, I I'm guaranteeing that design will remain unalterable after the production process. So it helps improve accuracy of the final dispositive, and it helps always to earn trust with your client, with your supplier, with your surgeon partner. So always remember that all the design decisions have to follow always and strictly the clinical decisions taken on behalf of the life quality patient. So always have the right confirmation of your surgeon responsible for applying and using the dispositive. So that's everything. Thanks again. These are my contacts. Thanks again to the DSP and DSG group. Thanks, Roland, for this first global meet, and thanks all of you for listening. If you have any question, please feel free to ask.
Okay, thank you.